This video is brought to you by us, RealPARS. Join the top 1% of PLC programmers. Learn from the world's best so you can join their rank. Head on over to realpars.com and start learning now. Welcome to Part 2 of Variable Frequency Drives Explained. You can find the link to Part 1 in the video description. As we have learned in the previous lesson, there are many applications where, in order to meet varying demand, motors need to throttle down output. Additionally, constantly running a motor at its full speed can be costly. A variable frequency drive is a type of controller that has the function of driving an electric motor by varying the frequency and voltage that is supplied to control its speed and power. VFDs are widely used in both industrial and commercial applications, such as control of fans, pumps, compressors, HVACs, and even roller coasters. Going back to the VFD diagram we were previously studying in Part 1 and quickly recapping, firstly, the VFD checks for a ground fault. Next, the alternating current input power is converted into direct current by the 6-pulse rectifier or converter, resulting in a DC waveform. Following comes the DC bus, but to prevent any inrush damage, the pre-charge circuit slows the change rate of the bus capacitors during power-up. The DC bus then filters and buffers the signal, which now follows the last step of the VFD's drive output, the IGBT module. We know that this last step will then convert the direct current into the alternating current as a pulse-width modulated output. But what does that mean? And how does that happen? It is impossible to talk about VFDs and insulated gate bipolar transistors, also known as IGBTs, without understanding what pulse width modulation, or PWM, is. An analog input signal can be modulated by generating variable width pulses to represent its amplitude. In a very brief summary, PWM is a way to control analog signals with a digital output. To understand the IGBT's function in a VFD, it is important to understand how an IGBT works singularly. At the simplest level, an insulated gate bipolar transistor, or IGBT, is a switch used to allow power to flow when it is turned on, and to stop when it is turned off. It is important to note, however, that they have the capability of switching on and off several thousand times every second. An IGBT is a solid-state device, which means it has no moving parts. Rather than opening and closing a physical connection, it is operated by applying a voltage to a semiconductor component, called a gate, that changes its properties to create or block an electrical path. Let's look closely at a typical IGBT. Its terminals represent the gate, the collector, and the emitter. Current flows along the conductance path composed by the collector and the emitter, while the gate controls the device. Here's an electrical drawing representation of it. The IGBT behaves similarly to a switch. As the word itself suggests, when a positive voltage is applied, the gate will close, or turn on, allowing current to flow between the collector and the emitter. If not enough voltage is applied, the gate remains open, or turned off, not allowing for any current to flow between the collector and the emitter. To prevent the device from closing, this voltage is kept negative in this off state. Now that we have an understanding of how our IGBTs work, let's go back to the application of IGBTs in VFDs, and let's represent our IGBTs as contact switches for simpler understanding. The top IGBTs, which in our representation are switches, are in the positive DC bus, and the lowers are in the negative DC bus. So when one of the top switches is closed, that motor phase and voltage then become positive. On the other hand, when one of the lower switches is closed, that motor phase and voltage then become negative. Therefore, by controlling the speed and sequence that those switches open and close, we can control the phases and frequency of our signal, 0, negative, or positive. It is important to note that VFD's output signal is a PWM signal, which turns out to be a rectangular waveform. This wave is crucial in the operation of a VFD as it is this variable voltage and frequency that will enable the VFD to control the motor speed. The control processor of a VFD contains a program that is not typically user-accessible. However, there are many parameters and settings that can be adjusted and tuned for optimal VFD operation for each application where it's been used to meet specific motor and driven equipment specifications and needs. The following are common adjustable parameters and settings in a VFD. Tunable, proportional, integral, derivative, or PID. Minimum and maximum speed, and current limit, among many others. The number of parameters varies based on the level of complexity of the VFD. They can range from 50 to over 200 parameters. Now let's combine and review once again what we have learned. Variable frequency drives are motor controller devices used in numerous applications, from small appliances to large compressors, and much more in between. The main function of the VFD is to drive and control motor speed and torque to meet application requirements by varying supply voltage and frequency. There are multiple stages inside a VFD controller, which can be briefly summarized as: drive input stage is when the alternating current is being fed into the inverter. For housekeeping, current transformers measure and compare current entering and leaving VFD, checking for ground faults. Also, initial inrush damage is prevented by the use of a pre-charged circuit. During the drive and drive output stage, the alternating current then gets converted into direct current by the 6-pulse rectifier or converter. This direct current gets buffered and filtered in the DC bus, where its resistor function is to divide voltage and to guarantee that all capacitors have the same voltage. Also, that this now filtered direct current can get converted once again into alternating current by the IGBTs acting similarly to switches allowing control of the phases and frequency of our signal in form of pulse width modulated output. Lastly, the motor and drivetrain stage is when this pulse width modulated output then allows for the control of the motor speed and consequently its mechanical output. VFDs have evolved tremendously. They have developed into highly sophisticated high-frequency power devices in the form of microprocessor controllers. The use of VFDs allows for predictable, smoother, durable, and highly efficient operation processes. Want to learn PLC programming in an easy-to-understand format and take your career to the next level? Head on over to realpars.com.